Hola.
¿Ya están lista?
Lista.
Voy a tocar la campana.
¿Y todos van a venir?
No porque ese horario no están El problema es que hay consejo interno.
Wow.
Y el consejo es hasta las 12 y siempre es hasta las 12 en Colombia. Pero por hoy se hizo la excepción porque habían dos. Y ninguno de las dos se dio, entonces a las 11 está bien. No muchas personas. Inclusive, ¿cómo se llama?
Maritza.
No, que trabaja también en materias en Venezuela. Él lo está en el consejo interno, es miembro del consejo. Tendrá que salirse, o a menos que lo decidan acabar. Bueno, yo ya vengo y me das unas palabras para presentarte, ¿te parece?
Sale.
Ok, perfecto. Ya voy a tocar la campana. Estamos aquí esperando que la chica de 25 años. Yo no te había calculado 24, pero Mariana, yo cumplí mi palabra.
¿Ya ven por qué no les digo la edad?
Yo te sigo haciendo bien. Hasta el último momento. Yo creo que esto era
Qué mal.
una proeza. Muy joven, ¿no? Muy
Sí.
joven a esta Auditorio. No, bueno, el tema también, digo. Muy bien. Yo tengo que escribir algo seriamente.
A ver si vienen.
No, es mañana. Es para mañana. Ah, yo creí que era hoy. Y es mañana. Entonces tú te quieres quedar. Sí, tienes que hacer la solicitud. Tienes un buen de chamba. Si quieres yo me voy, pero tienes un buen de chamba. Tómale la palabra. Tómale la palabra. Ahora, vienes también de divulgación, es probable que yo sí iba a ir hoy a la tribuna. No voy yo, mañana estoy abogado con el candidato. Pero vienes, ponemos equipo antes de que yo me vaya. Porque tú tienes que estar en el eso. Entonces sería bueno solicitar. Tómale la palabra. ¿Y si se puede o nomás por eso? Sí se puede, seguro. Sí, pero sí tiene que solicitar. Te lo comento, haz un paréntesis, ahorita más. Se puede, porque es una necesidad del momento. Que a mí me está necesitando. Sí, pero lo tienes que pedir el jefe. Sí. Si no te obligan a ir. Sí, y a mí moralmente me están. Vamos a ir a bajar juntos y ya está. Ya te vas a publicar. Esa es otra historia. Pues no, son historias que cambian. Tengo que ser memoria, ¿puedes escribir? No me esperes. Sí, tómate la palabra. Trata de ti. No es rara, ¿eh? No es rara. Claro. Mañana va a estar con la circunferencia desde las 10 y 11 hasta las 2 de la tarde. Te apoyo totalmente. Conmigo. Te apoyo totalmente. Y le digo a Javier. ¿Lo apoyas a mí o lo apoyas a él? Tú dime. Tú eres más rudo. Yo te apoyo a mí. Vale, madre. Eso, pinche Rafael. Gracias, Rafael. Caramba, qué entusiasmo. Es lo que me está contando. No he leído tu correo, ahorita lo leo. Que veamos lo que nosotros hacer una transmisión a meteorita. No, de la meteorita no se puede. Habrá que a ver si por la cámara si. No se puede. No se puede. Al auditorio vivo. Hola. Ahora lo que comentas.
Hola. El primero.
Los primeros y los dos.
Claro.
Eso no se puede. Lo que acordamos ayer con Liliana, porque Liliana estaba Javier, fue que iban a hacer ahí porque iban a poner en la materia. Ahí conectar la pantalla y la transmitirlo, eso es algo nuevo y técnicamente pasen al auditorio. Pero la gente va a estar segura que no hará presiones. No sé, la verdad.
Gracias. Ahorita me sirvo más café.
¿Cómo te presentan?
Pues, ¿qué tanto dicen? ¿Dicen mucho?
3, 4 oraciones que dónde terminó el doctorado, dónde trabajas, de cuándo trabajas. Bueno,
Ok, Instituto de Física hace un año.
hace un año.
Postdoctorado en Carnegie Mellon, Pittsburgh.
¿En dónde?
Carnegie Mellon.
Eso es en Pittsburgh, ¿no?
Ujú. Y doctorado en París 7, de Diderot, en Francia. ¿Y qué más? Trabajo con censos de galaxias, no sé qué. Pero eso yo lo voy a decir.
Cúmulos.
No, censos de galaxias, sondeos de galaxias.
Materia
Ajá.
oscura trabajas tú, ¿no?
Mm,
No.
Voy a hablar más de energía oscura. Si quieres ya no digas más, yo digo más. Ajá.
No, no más.
Yo creo con eso. Ujú. O sea, tengo trabajando en consensos, sondas de galaxias mucho tiempo. Pero no lo digas, yo lo digo. Don't
¿En
worry.
inglés? Sí.
No sé, eso te iba a preguntar. ¿Qué quieren? ¿En inglés? O sea, si no hay mucha gente, les pregunto, pero da igual un poco. ¿En qué lo suelen hacer?
Depende del público. O como el expositor se sienta mejor.
Como quieras.
Si no hay problema por el idioma,
Mm.
entonces preguntando. Pues algunos sí la preparan en español, sino de plano la hablan en español. O si la preparan en inglés, entonces de plano en inglés.
Da igual.
Tienes 40. Esperemos 5 meses que estar haciendo.
Eso me dijeron, pero sabes que yo había preparado para una hora, pero bueno.
No, fíjate que no puedes. Ahorita a las 11, a las 12 empieza otra. O sea, sí se podría en el sentido de que
Normalmente
normalmente a las 12 y esto está, todo el mundo está interesado en el instituto y va a haber bastante.
sí. Ya, hola, me dije, al menos alguien de... si no venías ya.
Esperemos 5 minutos, ¿no?
Sí, y va a tener que terminar a las 12, ¿no?
Sí, no antes.
Deberían haber hecho.
Es que quieren que termine antes, pero entonces ahora no sé qué va a hacer.
Sí, porque va a haber va a haber 15 minutos de alguien que va a hacer va a haber unas instrucciones de un taller que se va a hacer en la after party.
Sí.
Y después de los 15 minutos empieza la exposición verdadera.
Ajá. No, pero siempre se retrasa todo entonces. Sí, es fácil.
Pues sí, todo lo retrasan y ya está.
Yo sé que esas están bastante, ¿cómo se llama? Las de G4G van a ser bastante controversiales, entonces
Ah, sí.
esa es la situación. Sí, pero no, no, está bien. Pero
No, pues si no, hasta donde llegue y ya está, ¿no?
sí, yo me paro.
Me avisas 10 antes
10 antes.
para ver qué me salto, ¿sale?
Bueno, sí, te aviso 10 antes.
Porque tengo muchas transiciones y luego hablo muy rápido y puede irse rápido.
Consensus.
¡Ey!
¿Español o inglés?
Inglés. I already have. Bueno, pero es que si empezamos 5 tarde me da 5 más, ¿eh?
Bueno, buenos días a todos. Buenos días a todos. ¿Sí? Ok, no, para mí.
Ah, ok.
Buenos días a todos, gracias por venir. La asistencia pues no es mucha en este momento.
No.
Todos están en consejo interno. Y esto debido a que va a haber otra exposición y va a haber un taller. Después van a ver va a estar bastante apretada la agenda. Entonces también se están preparando para la otra, que sí va a ser de pronto un poco más de discusión. El día de hoy nos visita el del Departamento de Física, del Instituto de Física, Mariana Vargas. Hace un año, un poco más de un año, está trabajando en el Instituto de Física. Ella hizo la licenciatura aquí en el Instituto de Física, luego hizo el doctorado en París 7 en Francia, luego se movió, hizo un postdoc ¿dónde fue?
En Carnegie Mellon.
Eso. Carnegie Mellon. Entonces hoy nos va a hablar acerca más de energía oscura. Ese es el título.
Bueno, me parece.
Pues adelante.
Gracias. So I'm going to switch to English because I think at least one person there is not speaking Spanish. So the seminar for today is about using galaxy surveys for learning about cosmology, in particular about dark energy problems. So I'm going to try to go very fast because I was planning to do a seminar for 60 minutes and I have to switch to 45. So I'm going to be very fast in a bunch of material, but I hope you can understand anyways. So I'm going to start explaining what is the motivation of this research, that is understanding something more about dark energy. Then I'm going to pass directly to the observable that we use for doing this, that are basically two, baryonic acoustic oscillations and redshift space distortions. And then I'm going to go briefly to talk about different surveys that I have been involved. I'm going to start focusing on the result of eBOSS, the last eBOSS results that have been published about a month ago. And then I'm going to go very fast to the part of eBOSS and DESI as the future of these galaxy surveys and dark energy problem. So to start, it's simple for me to start talking about what is the status of cosmology today, at least from my point of view. I think there is a consensus in the cosmology community about what is the best model that we have to describe the universe today. So this model is called lambda CDM, and the strongest points of this model is that it's the most simple model that we have to describe the universe. And I think the most important point of this model is that it's in agreement with the most of the observations. So in particular, the most robust one that are supernovas BAO and CMB are in agreement with this model, and I think this is the most strongest point of this model. So this model consider three components: this dark energy, cold dark matter, and baryonic matter, and also consider this initial period of inflation that explains this growth of initial perturbation that produces the structure that we see today. So to show this remarkable convergence of these observables around this model, I used to present this plot where we have all these contour plots that are showing what are the best parameters that describe our universe. And we can see the three observables that I'm talking about, CMB, BAO, and supernova, and all of them are converging in a very small region of the space, parameter space, telling us what is the energetic content of the universe today. So if we see the numbers, there are not exactly these numbers, but we will see that our universe is dominated by this dark energy, and then we have this dark matter in 23%, and we have only a small percentage that we know that is the ordinary matter that we know. So that tells us what are the important questions today in cosmology that are basically, I will say, three. The first of them is telling what is the nature of dark matter, what is the nature of this dark energy, and what happened in the early universe. So I'm going to focus in the second question, that is what is the nature of dark energy. And for that, I'm going to only briefly say that in the rest of the talk, I'm going to continue saying dark energy as a synonymous of cosmic acceleration. But in general, dark energy, we can think just like a way to solving this problem of accelerated expansion. So for explaining the accelerated expansion, we have many possibilities. We can go directly to the equation of Einstein, and if we modify the right side of the equation, introducing a new tensor momentum, we will have new components for describing this cosmic acceleration. If we decide to modify the left side, we will interpret this modification as a geometric property. But we have many possibilities for explaining this cosmic acceleration. So in the side of new components, we have different models for this dark energy. And in the other side, modifying the theory, adding models, extra dimensions, or changing the gravity part, or changing the cosmological principle, allowing inhomogeneous universe. All of them could explain this cosmic acceleration. So the idea of us as observational cosmologists is to try to constrain this jungle of models and say what is the best model that is in agreement with the observation. So for that, what we do is to take a phenomenological approach. What it means is that we are going to use an equation for describing this new component, an equation of perfect fluid, and we are going to put some conditions to observe this acceleration of the expansion, and then we are going to try to answer very simple questions. So the first question that we are going to ask is if this, the equation of state of this new component is constant in time. So we'll have a cosmological constant, in particular, one particular solution. that will give us an energy density that is constant in time, or we can think about a more general equation of state where we are going to describe only using two parameters just because we are trying to use observation to constrain these two parameters, and we are trying to answer if this equation state is evolving in time or not. So that are the possibilities. What we are going to do with observation is trying to constrain these two parameters of the equation state of dark energy. So with this is the introductory part of what is the motivation, that is dark energy. So we are going to pass directly to the observables. The observables, we are going to use the large-scale structure of the universe for constraining the cosmology. In particular, when we study the dark energy, we have two kinds of proofs to trying to explore dark energy. Those related to measurements of distance, that the supernova and the baryonic acoustic oscillations, and those related with the measurement of the structure, like the clusters, the weak lensing, and the redshift space distortions. So I'm going to focus in these two that we can use using galaxy surveys. I'm going to start explaining what is the baryonic acoustic oscillation that I already said is related with these distant measurements, these geometrical measurements. So the idea of these proofs is that we are using distance to disentangle between different cosmological models. So here you can see different lines are different kind of distance in cosmology, and different kind of lines are showing the same distance computed with different cosmology. So you can see how measuring distance is very sensible to disentangle between different cosmological models. And this dependency comes through the Hubble parameter that is depending on the energetic content of the universe. So we're going to use this measure of the distance, and in particular, we are going to use what we call a standard ruler. And a standard ruler means that we are going to use a pattern that we know from first principle what is the value, and we are going to measure the apparent size of this scale at different times, and with that we are going to explore what is the expansion history of the universe. This is very analogous to what is done in the supernova with the luminous distance. So the idea now is to explain how this scale is imprinted in the universe, and I'm going to explain now how this scale was imprinted in the universe, in the distribution of matter of the universe. So the baryonic acoustic oscillation, to understand that, we need to go to the early universe, and we need to think if we are in one of these overdensities, the small overdensities at the early beginning. And at this time, we have all the components. We have the baryons and the photons and the dark matter. And we know that baryons and the photons were kind of coupled in this plasma. So in this plasma, what happened is that the competition between gravitational collapse and radiation pressure that is opposing to this gravitational collapse generates an spherical waves that start to propagate since this moment until the decoupling time, as we can see here. So this spherical wave continue propagating until the decoupling time. At this moment, the photons decouple from the baryons, and the baryons get frozen at this characteristic scale, that is the scale of BAO. So what it makes the characteristic pattern that we are going to look in the distribution of matter of the universe is the gravitational interaction between dark matter and baryons that will give us this final configuration where we have every single initial perturbation surrounded by this spherical shell around the scale of BAO. So what happened next is that the galaxies will form basically in these overdensities, and we are going to try to look this characteristic scale in the universe. But the problem is that I explained this for only one overdensity. If we think that this happened in every single overdensity, the only way to look for this pattern to this scale is looking in a statistical way. So what we're going to think is we are going to use the galaxies that form in these overdensities, and we are going to look at characteristic scale of separation between these galaxies that would tell us something about this characteristic scale. So the tool what we use is the two-point correlation function. If we do the two-point correlation function, the BAO feature will appear as a peak at a characteristic scale, that is the scale of BAO. So the idea of this is then use different samples that are in different redshifts and to try to use this scale for exploring the expansion history of the universe. So just to mention what is the two-point correlation function, the way to interpret this is if we have two volumes separated by a distant r, the correlation function will tell us the probability of having a galaxy in the second volume, given that we have this volume separated by this distant r. So it's giving us a measurement of the clustering of galaxies. So if we separate the separation between two distances in two components along the line of sight and across the line of sight, we can compute the two-point correlation function in 2 dimensions, and that will be the source of all the analysis that I'm going to talk about later. So this is the two-point correlation function. This is the direction perpendicular to the line of sight. This is the direction parallel to the line of sight. And here, I think you can see, maybe, this ring is the BAO feature that early on you have seen like a peak in the two-point correlation function. So now I'm going to pass to the second observable, that is the redshift space distortion. And again, I'm saying we are going to use the same kind of information, the two-point correlation function that encodes all this information. So what are the redshift space distortion? The idea is if we have the observer here and we are seeing of these galaxies, what we see in real life is the redshift. So the redshift is telling us something about the radial direction of the galaxy, but it's also polluted, it's contaminated with a peculiar velocity. So this peculiar velocity is distortion, the way that we are measuring this radial distance. So the galaxies that are falling through the potentials will look clustered instead of the real position that they have in real life. So when we compare this pattern in the in the points, that is what we will see in real life with radial positions that we can measure, but what we see is this, that is the distortion related with this fact that the positions are contaminated with the peculiar velocities. So that reflects in the two-point correlation function broken the isotropy of this figure. So we can see these distortions, and the good news is that we can use this distortion to study something else than the baryonic acoustic feature. And in this case, it will give us information about the growth factor, that is the growth of a structure. So just to give you a feeling how we can understand study cosmology using the growth factor, you can see here 2 different models, cosmological models, how the growth of a structure happened in a different way. So this dependency of the growth factor in the cosmology can tell us something about the cosmological model behind the observations. So here we have the classical plot where we have this growth factor as a function of the redshift. As you can see, different models, and it's clear how measuring this growth factor at different redshifts can help us to discriminate in all these cosmological models. So again, the source of all this information is this two-point correlation function, but instead of just looking for the ring of this two-point correlation function, we are going to fit the whole shape of this two-point correlation function, that is all this figure. So now you have all the tools to understand what we do with galaxy surveys, so I'm going to go directly to galaxy surveys. I'm going to show very fast this movie that is showing real data. It's a visualization of SDSS-III, and you can see all the galaxies that were measured for this release. I don't remember what it is, but you can clearly see the structure that we're going to use to learn about cosmology. I'm going to pass because if not, I will not have enough time to finish. So I'm going to start with, I'm going to talk about 3 different surveys. So we have here all the dark energy experiments from 13 to 31. And in these red lines, we have the 3 surveys that I'm going to talk about here. So I'm going to start with BOSS. BOSS is something that took data from I'm gonna say more, but it's already done. So I'm gonna show the final results of BOSS. Then I'm gonna talk about eBOSS that is just starting. We have already 2 years of data, and we're gonna start doing amazing science. Miguel here is going to do it. And then we're gonna have the opportunity to also talk about a little bit of DESI, that is the future of these galaxy surveys. So I'm gonna start with BOSS. BOSS took place from 2008 to 2014 using this telescope that is the same as eBOSS, this spectrograph, and all these technical details. The main goal of BOSS was to measure the BO position with a precision of percent using the galaxies, and also with 1.5 using the quasars. I'm gonna focus in the result of the galaxies that are the latest results that we just submitted to the journals. And the goal was this precision using this sample of galaxies that is median redshift is 0.6. And we measuring a total of 1.2 millions of luminous red galaxies. So this was the progress of the survey all this time. These are the final data release. We have 2 set of papers, so I'm gonna focus in the final set of papers that are using the complete data of BOSS. Previously, in December of last year, we released another set of papers that are using a little bit less data. So I'm gonna focus all the presentation on BOSS in one paper that is the most important paper of BOSS. Is the alphabetical paper that is concatenating all the results of all the different groups working in the galaxy clustering group. And I just wanna mention that you can see a lot of authors here, but I'm sure that every single author in this list have contributed to this work. It's a very rich work, it's a very complicated work, and all the people here contributed in a certain way in a certain period of the survey. So this paper is the culmination of the whole BOSS collaboration working in the galaxy surveys. So it's the conclusion. I'm gonna start with the conclusion. I just want to highlight that, and it's all the people that was working on this galaxy, on BOSS in general. So this alphabetical paper comes with 11 supporting papers. Each of these 11 supporting papers is integrated in this alphabetical paper and is doing a particular analysis that is in this alphabetical paper. So for example, in blue, we have all the BO analysis. In green, we have all the full shape analysis, or redshift space distortion analysis. And in this other color, and I don't know what it is, we have other supporting papers that are doing mocks or catalogs or some particular technique that was used in the final analysis. Also, we have another set of papers, all of them released the same date, of companion papers that were not integrated in this alphabetical paper, but they are contributing with different analyses, usually not compatible with the official one. Not compatible to integrated, but obviously compatible in terms of science. So what is new of this final BOSS paper? So here we have the samples, the original samples of BOSS. One is CMAS, and this blue is the low C. So instead of using the classical samples of eBOSS, we combine it optimally. We combine the 2 samples, and we divide it in 3 redshift beams. These are the redshift beams, 0.2 to 0.5, 0.4 to 0.6, and 0.5 to 0.75. So they are overlapping beams of redshift, and the analysis was performed in these 3 different samples.
But all these are red galaxies?
Sorry?
Are red galaxies in this?
See, luminous red galaxies are basically low C and CMAS, both of them. The difference is that one is a lower redshift and the other are supposed to have the same mass. That's why the name of CMAS. But we combine everything together. This is kind of all the steps that we need to follow to do the analysis. I'm not going to go to all these steps, but all these steps are included in the analysis, from the target selection, observational systematics, correction, simulations, covariance, fitting, reconstruction, cosmological constraints. I'm gonna go directly to the results. I'm gonna go I'm going to try to guide you to all these papers if you are interested, so you can take a look by yourselves. So I'm going to start with these two papers. Red et al. Is describing all the large-scale catalogs that we used for all these final analysis. Kitaura et al. Is describing all the mocks that we produced as a collaboration to perform all these analyses. Then these papers that we have here are all the BAO papers. As I'm mostly focused in the part of BAO, I'm gonna be biased to describe more these BAO papers. And then we will have the other, I'm gonna go later with the greens that are the RSD papers. So for the BAO measurements, we have different ways of computing the two-point statistics. In general, if we do it in configuration space, we will have this correlation function, the two-dimensional that we see before. We projected using the Legendre polynomials, and we have this monopole and quadrupole, and the three lines are the three different redshifts. They are just one over the other for visual clarity. In the other side, we have the power spectrum analysis. That is the Fourier transform of the two-point correlation function. But when we apply this to data, they have completely different systematics, so they are not giving us exactly the same information. That's why it's important to do different estimators and different spaces to complete the analysis. So we have this paper of Butler et al. That developed all the technique for performing this BAO analysis in Fourier space using the multiples in Fourier space. We have this Roth et al. Doing the same but in configuration space and also exploring the observational systematics. We have then my paper that is focusing also in doing the BAO measurements, but this time again in configuration space, but focusing in the theoretical systematics. And then for understanding my paper, I need to go back a little bit of how we do this fitting of the two-point correlation function. So the idea is very simple. We have this projection of the two-point correlation function in 2 dimensions, and we project it using the Legendre polynomials or any other projection that we want. In particular, here we use the Legendre polynomials. Then we have this monopole and this quadrupole. And then to fit this two-point correlation function, what we care only when we do BAO analysis is the position of the peak. So we are going to prepare a template that will depend of 2 parameters, alpha and epsilon, that are just decaling the peak. And as all the information of BAO is in the position of the peak, the constraints on alpha and epsilon will traduce directly to constraints in the angular diameter distance and the Hubble parameter distance. So the idea is that in the theoretical systematics, we are exploring all the possible sources of systematics that can affect these best fit parameters and try to produce an error budget that will tell us the final systematic error that we are going to add to our measurement. So this is just to show how we do the things, but at the end of the day, we have a bunch of tables with a bunch of numbers, and all these numbers are a contribution to the error budget given a particular systematic that we analyze. So in this case, for example, we are using different two-point statistic estimators in configuration space, and that is giving us an idea of how these different estimators are contributing to the error budget. So you will find a lot of these kind of tests in this paper. But at the end, we will have, from these 3 papers that I just mentioned, Butler, Ashley, Ross, and my paper, we will have 3 different measurements of BAO using slightly different techniques. So we will see later that the way to combine these measurements, but here in this plot, I'm just showing that the 3 analyses are giving completely consistent results, and that is one important point of this paper, that is showing the robustness of the BAO technique applied to these galaxy surveys. So we have here the 3 measurements for the 3 redshift beams that we analyzed. This is analogous to the angular distance, and this is the Hubble parameter distance. And you will have here the yellow point is the consensus of combining all these measurements, the consensus measurement that we will use at the end for the infer the cosmological parameters. So now we are going to pass briefly also to the analysis in the full shape analysis, that is not just considering the position of the peak, but fitting the whole shape of the two-point correlation function of the power spectrum. And this is what we have from data This is in configuration space. This is in Fourier space. How we get the final result from the data, the two-point correlation function and the power spectrum of the data. So we are gonna fit this. We have 4 different analyses, again using different estimators. Here we have multiples in Fourier space, wedges, that is a different projection of, instead of using Legendre polynomials, we are integrating in mu. Here we have the analogous wedges in Fourier space and the multiples in configuration space. So again, different estimators, different models, different choices of parameters, and all of them will end at the end with one point in these three plots. The first, again, is the angular diameter distance, the Hubble parameter distance, and this time, as we are doing this full shape analysis, we will have a measurement of the growth rate times sigma 8. So that is the result of doing the full shape analysis. We have all the points that are also pretty consistent between them. And again, we will have the consensus is the black in this case. I don't think, no, the consensus is this red. So at the end, we combine all these analyses together to have one single point for each.
What are the cosmological parameters of this model?
we go there. we go. I'm
fast question.
Mm-hmm.
The Hubble distance and the angular diameter distance, they constrain the same thing, are not repetitive?
No.
Or they are giving different restrictions?
In fact, they are complementary. As you know, the distance of both parameters depend differently on the cosmological parameters, so they are giving complementary information in general. You will see that later.
Excuse me.
Yeah.
Can I make another question? Will you comment on the dispersion of the measurements compared to, let's say, the other methods to determine the difference in the cosmological models?
Okay.
Because you are working until now at low regis.
Mm-hmm.
So I would like to know what is the dispersion or the possibility to differentiate between,
Cosmological parameters.
yes,
I-
compared to supernova, compared to
I'm going there.
Baryon H2, compared to Newton
I-
quasars.
Okay. I'm going to show the cosmology part just next to these 2 plots. Just wait for me 1 minute.
Can I ask you just one question that is related?
Yes.
How do you obtain the consensus value?
I'm going to also say something. Just a word. Because I eliminated this slide. Sorry? I'm going very fast, sorry. But yeah. So this paper, Sanchez et al., is a paper that is devoted to say how we combine all these different constraints. So the main idea is that in a perfect world, if we do the analysis in Fourier space or in configuration space, the result should be completely correlated because one is the Fourier transform of the other. But this doesn't happen, right? So what we do is we use all these and make a huge covariance between all the parameters, and then we use algebra to put all the information to find a basis where just this one parameter, consensus parameter, will be a combination of all these other results that are just using these properties of covariance of the different parameters. I skipped the slide about that, but it's completely straightforward if you follow the questions. So it's just doing that. At the end, we have all these big covariance. All the parameters are covariant with everything, and we just reduce it to compact all the information in a single parameter. So at the end, we finish with 3 points and then we are going to use these 3 points for infer cosmological parameters. We haven't done that yet. We just have a measurement of the angular diameter distance, Hubble parameter distance, and growth factor in 3 redshift beams for the case of RSD, and we have also that for the BAO, and also they are given different information. They are not given the same information. Even the angular diameter distance coming from the BAO analysis is not giving exactly the same information of the RSD angular diameter distance, because they are fitting different parts of the correlation function, and they are sensible to different, in a different way to the cosmological parameters. So at the end, we finished with this point, 3 points here. This is this work, and the 3 lines are the different kind of distance in cosmology, and you have all other points of other BAO experiments that there are in the world. And then we have the same for the growth factor. We have 3 points and all other points from other measurements, in this case, just using SDS data. And you have all this, and we are going to use that to infer at the end cosmological parameters. But this is just the last step. So at the last step, we are using these points, instead not these points, but the livelihoods complete, and we are using them to putting them in a MCMC machinery and get the cosmological parameters that are consistent with these observations. And in general, we don't present the BAO results alone. We combine with all these supernova measurements and CMB measurements to get the tightest constraint on the cosmological parameters. So I'm going to show just 2 plots of cosmological parameters, because you have a bunch in the paper, but I think those are related with the dark energy. In the left side, we have the constant parameter of the equation state of dark energy and the curvature. We have, in green, Planck plus supernovae. In gray, we have Planck with BAO only, not using supernovae. And then we have, in red, using BAO full shape analysis, redshift space distortion, that means, and CMB. And when we combine everything, we have the blue contours that give us like the best constraints of these parameters that we have up to now. So we have, if we see the numbers, that is pretty consistent with a cosmological constant and a curvature, a flat universe. In the other side, we have an extended model where we allow this omega A to vary, and then we have the same color code. The blue contours will tell us the best constraints that we have up to now on these parameters, and you will see that are around the values of a cosmological constant. In this case, see, but you can see in the paper there is also the case allowing and you all will have just these contours to grow up a little bit, but it will be around, again, the same parameters. So you are going to the point, and this is the point of all next future experiments, is to constrain better these cosmological constraints on the equation state of dark energy. And that's why I'm going to speak the conclusion, because I already said at the beginning, we finished something that had been 10 years of work. So now work is not over, hopefully for us, and we have this next step that is eBOSS. So eBOSS is the last experiment in the third category. Well, okay, perfect. Of stage 3 experiments. That means that we have certain prediction for the incertitude that we expect from this experiment. This experiment is here. It's just here that we are going to have the same precision as we have for BOSS, but the idea is that we will have other redshifts, other points in this plots that we said before. So that is very important, and that is the importance of eBOSS. Yes? No? Nothing? Okay, Miguel. So also it's a big collaboration of people here. Hopefully a lot of people here also is working on this. And this is BOSS, how is extending what we have measured up to now with BOSS. The difference that I think are the most important are highlighted in red. So we have different tracers. The different tracers we are using for the first time ELGs, emission line galaxies, so we don't know how to do it very well. There is a lot of work in this side. We have, for the first time, a quasar sample for doing cosmology. So the first paper doing clustering with quasars will be this. Then we have the precision expected with these 2 2 new tracers. So that is the new thing of eBOSS. We have also the LRG sample that we already know how to do it because we have been doing LRGs from 10 years or 15.
All galaxies are emission line. You mean Lyman alpha emitters?
Emission line galaxies, I think.
No. Most of galaxies are emission.
Okay.
No.
You know better than me.
You mean Lyman alpha emitters?
No, I don't mean Lyman alpha. I don't mean that, but I'm not a specialist of emission line galaxies. Is any specialist here?
Well, simply, of course, not all galaxies are emission line galaxies. Galaxies have absorption spectra. Emission only.
This is a homework for me, okay? Vladimir, next seminar, I'm gonna tell you. So this is important for us because it's the program of the strategy of observation. So for the first 2 years, they are focusing in observing these LRG and quasars, and for the 4th year, will be devoted to the emission line galaxies, whatever they are, and then we will finish the quasar sample. So in particular, what we have up to now is this footprint. So these are the plates that have been taken up to now, and we have basically a bunch of LRGs and quasars. And then this is the footprint of the LRG sample. So you have here the North Galactic side and the South Galactic sample. These are the square degrees that we have up to now. These are the expected, so we are just starting. And these are the number of galaxies that we have up to now, very little, but this is enough to start doing some work of systematics. And then this is the final number that we expect to have for the LRGs. So this all, again, all the chain of analysis that we need to do. But in this case, we start working in this part, systematics, observational, and not exactly me, but one student start to work on this, that is working with me and Octavio, and he started exploring these systematics. This is from the BOSS, but I don't have the new one. These are different systematics in galactic extinction, air mass, etc. And what he is doing is trying to determine how these systematics are affecting the number density of galaxies. This is a lot of work, and at the end of the day, what we need to look is what is the effect in the two-point correlation function, because we need to guarantee that our correlation function is not affected by these systematics. So this is work in progress. We have also this quasar sample. These also are plots that are not generated by me. We have here Miguel. I have been working in this quasar sample. We have here the number density of quasars that we have up to now. You can see the median redshift is here, I don't know, around 1 point something, 7, something like that. This is the footprint, and the color code is the completeness. So the red means that we have all the quasars that we want to measure in this region, etc. And the blue one is that we haven't really measured yet this part. And using this quasar sample, we are working in this part that is using the simulations and fitting the correlation function of simulations to compute this covariance matrix, and also start to computing this two-point correlation function of quasars and try to fit this two-point correlation function. So these are also work in progress. We have here the first attempt that we have done of doing this two-point correlation function, but not me, Miguel. The two-point correlation function, monopole, quadrupole, the simulation mean, and the variance of the simulation that we have available up to now for doing this analysis. So we are there. I insist we have a lot of work to do in the future, but I'm gonna pass very fast just to the final part, that is DESI, that is the future. DESI is the first experiment on the fourth stage of experiments, dark energy experiments. That means that we are gonna decrease the error bar by an order of magnitude at least. This is the telescope where the measurements will be done. Everything, it's not important to go to the detail, but the telescope is bigger, more fibers, more everything, more spectrographs, more whatever. And then also this is the big collaboration. We have also, this is important for us because the the tracers that we are using in DESI, that we plan to use in DESI, are the same that those that we are using for eBOSS. So it will be a lot of feedback between eBOSS and DESI, hopefully. So all eBOSS will help us to prepare DESI in the future. In particular, the ELG part that we don't know yet pretty well. This is what we are now. This is the Hubble parameter in a particular divided by 1 plus set. And this is what we are now. So with eBOSS, we will fill these points in this plot. And with DESI, we will go to fill all these other points. So this is the power of all these two experiments that are coming now. This is the decrease of the error. So we are in BOSS here. We have here Euclid, that is another experiment that is going to happen. We have here black DESI. And we have eBOSS here that is complementary to what have been done by BOSS up to now. These are in terms of the constraints of dark energy. What we expect to have is BOSS is in gray. We're going to shrink the contour, the confidence contour of the dark energy parameters that we have here. And with DESI, we're going to shrink a little bit more these constraints. And the same for the growth factor. We have 3 points. This will be the 3 points that will be provided by eBOSS soon. And then this will be complemented by DESI with all other points in this growth rate plot. And with this, I finish. Just saying that this phrase that I like a lot, that is, we are just starting. We have a bunch of data that will come very soon. We need a lot of people to work on this data. And hopefully, people will be interested to start working on this. We are involved in 2 collaborations at least now, so it's good to have people working on this. So this is the message for the students. Obviously, the researchers.
Thanks, Mariana, for a nice presentation. Questions, comments, suggestions?
Yes, first of all, I want to apologize to Vladimir. I think there is a misunderstanding. He does know. So the sample is such that they are, in a way, emission line galaxies. But I think that what you mean is what has been done by Roberto Terlevich, who is using giant H2 galaxies to measure distances. I don't know. I would like you to clarify, or Vladimir, or because I would like to understand. Thank you. And then let me put the other one. Can you go back to the slide where you showed your wishful thinking with DESI on, no, that one. Mm-hmm. So why is there supposedly a larger dispersion between 1.5 and 2, and then it diminishes when you go further? The error bars.
This one.
Yes. Why do they decrease after 2? Before they increase again?
Okay, I'm going to answer my feeling, but I'm not certain about the answer. So we have different tracers. So my feeling is that this part is coming from a different tracer, and we expect a different precision of that tracer. So I didn't say, but I skipped a bunch of tracers that are the Lyman alpha forest that we are using also to measure BAO. The Lyman alpha forest, instead of using these quasars like points and studying the distribution of quasars, we are using like a backlight. And all the pixels between this quasar and us is contributing to our 2-point correlation function. It's a completely different technique and has larger errors. Everything is more complicated using this technique. Probably this part is related to that. Probably. I'm not sure. I'm just guessing. ELGs is also a sample that we don't know pretty well, and we expect to have larger errors. If we go back to the eBOSS slides, you will see that the expected error on ELGs, on BAO, is like 4%, when for ELGs is 1%, for example. And I think for Lyman alpha is 1.5. So my guess is that this part is ELGs.
First, I thank you for your presentation. A kind of quick for non-experts, but anyway, very illustrative. And this is exactly what, in some way, I was looking for. I think that all this information needs to be included in an extragalactic and cosmology course nowadays. And I find how to prepare and how to include all this material. I hope that you can help me to do that.
Sure.
This is also to emphasize the importance of the statistical properties of galaxies and how to connect with important topics. So that's it.
Thank you.
More questions, more comments? If there is,
Vladimir, a difficult one, I'm sure.
I noted in the results from eBOSS, from BOSS, that the constraints from the growth factor are different from those of the BAOs. So is this true? Because this is one of the main things I think this kind of projects are trying to see. These are two different methods to infer the same cosmological parameters. One is based on the growth factor is based on the gravitational clustering, the action of matter, gravitational. And the other one is geometrical, the BAOs. And so if there are different results in the cosmological parameters from one or other test, this is pointing out to, I think, we have to have another theory of
Another theory?
to extend general relativity, let's say. So I don't know, but I noted in your plots that the results were different from BAOs and growth factor. I don't know if the papers you discussed that.
Which plot? Well, I don't know which plot, but I'm gonna
Yeah, when you
something. More? This one?
Here, for example, you see here the blue lines are the lambda CDM. The constraints from the BAOs or half distance are in agreement with lambda CDM. But in the growth factor, there is a disagreement with the observations with, so they are giving different results.
Here, well, I think there are many things. So first, in these consensus values, we have already combined BAO and full shape analysis and RSD. So these 3 points and DA and Hubble parameter already include information of BAO. So if we go back a little bit and we compare the consensus from only full shape, only RSD, and no BAO, it will be different from this, a little bit. It's not exactly the same. So these are already integrating both informations. So the important point here is that RSD is giving us two informations. So we are doing two things. We are doing this growth factor measurement, and we are also doing Alco-Paczynski test, but at the smaller scales. And this Alco-Paczynski test applied at the smaller scales, if we compare with what we do with BAO, that is kind of Alco-Paczynski at large scales, they are giving different, not exactly the same information. I'm not gonna say different because it's tricky to say different, consistent, but not the same information. That is telling us that the fitting from these smaller scales that are the full shape analysis is providing extra information somehow compared with the BAO only. It should be related with the way we fit the models, whatever, but we need to, up to now, to combine both, because any of this analysis is giving us the total information. So we need to combine all of them. So this is one point. And the second point, and I'm finished, I promise. This plot could be interpreted in many ways. Many people is already happy saying that they are consistent within the error bars. I already noticed that you are not, but we have the two bunch of people. So yes, I think there is a lot of excitement of this point of the growth factor. This is the next thing that the people will really look for to understand, to see what happened there. But yes, you can see that it's slightly lower, but depends on people. For me, it's okay.
Okay, thanks again to Mariana for a nice talk. Sorry for all of you. We have another completely different topic now at 12. You are invited to attend